In this chapter, which is called Applications of Forces, we're basically going to have a look at how do we apply all of the concepts that we learned in chapter 5 about friction and resolving forces and slopes, and just apply it to lots of different contexts, essentially in different scenarios. We're going to do 2 lessons on what's called statics, which is basically things that are remaining still, and then 2 lessons on dynamics, which is basically things that are in motion and moving. Really, there's no difference. It's just that's the way that they are often categorized in these sort of problems. So here we're given a particle in the middle, and we're told that it's in equilibrium. If they say that something is in equilibrium, hopefully you already know that that means the forces are balanced. So overall, this particle is not accelerating. It could be moving, it's just that it's not accelerating. So the net force in any direction is 0. So what we can do is we can split up all of these forces so that they are just either vertical or horizontal, and then we can resolve vertically and resolve horizontally. So the only force that I need to deal with here is this P, which is at an angle of 30. So it's got one component here, which is going to be P sine 30, and then it's got a horizontal component of P cos 30 when I resolve it. And now I can just consider the forces vertically. So that would be Q plus P sine 30 equals 8. Or I suppose I could write minus 8 equals 0. Either would be fine. And then I can resolve to the right. So I've got 9 must be equal to P cos 30. So those are my 2 equations. Now I can start solving those. I think the bottom equation is quite easy to solve. So I can do 9 divided by cos 30. So P is 6 root 3. Then I can put that into the top equation. So Q plus 6 root 3 sine 30 equals 8. 6 root 3 times sine 30 is going to be 3 root 3. And then 8 minus that will be Q. So Q is 8 minus 3 root 3. Or if you wanted these as decimals, it's about 2.8 for Q. And 6 root 3 is about 10.4. And these are obviously in newtons because they are forces. So these are the required forces for P and Q to keep this object in equilibrium, so to have 0 net force. Let's have a look at another couple. So we've got the same scenario here. This object is in equilibrium. This time we've only got one force that's horizontal. We've got to resolve Q and we've got to resolve this 6. So let's deal with the 6 first of all. So this component here, which goes downwards, is going to be 6 sine 45. And this component here is going to be 6 cos 45. Now the Q we need to resolve. I'll do that in a different colour. So this component here is going to be Q, but we don't know this angle here. I suppose we can just work it out. If this is 120, this must be 60, just because angles on a straight line add up to 180. So this is Q sine 60. And then horizontally, we have got Q cos 60. And now we can do our resolving. So vertically, we have got Q sine 60 must be equal to 6 sine 45 if they're in equilibrium. So I could actually solve that now, couldn't I? Q is going to be 6 sine 45 divided by sine 60. Let's see what we get. We get 2 root 6. Well, that is about 4.9. If we resolve horizontally, what I'm going to do to the right, we've got Q cos 60 plus 6 cos 45, because they're both in the same direction to the right. They must be equal and opposite to force P. And now I can solve this. So I've got 2 root 6, which is q, times cos 60, plus 6 cos 45. That means that p as an exact answer would be root 6 plus 3 root 2, or as a decimal, that is 6.7 approximately. There we are. So we'll go at another one. So we need to resolve this force P. So the vertical component is going to be P sine theta. I'm assuming in this question we're also going to have to work out theta as well as P. And this is P cos theta. We need to resolve the 9. So the vertical component is going to be, not P, 9 sine 40. The horizontal component is going to be 9 cos 40. Let's go for another colour. This force here, the 8, the downwards force is going to be 8 cos 20. Goes adjacent. And this one here, which is opposite, is going to be 8 sine 20. And now we can resolve. So let's do vertical first. So vertically, P sine theta plus 9 sine 40 must be equal and opposite to 8 cos 20. So that means that P sine theta is equal to, I'm just going to move the 9 sine 40 to the other side. So we've got 8 cos 20 minus 9 sine 40, which gives me 1.732. Do it to a few decimal places. We resolve horizontally. We've got 3, just this horizontal force of 3, plus 9 cos 40. And then we've got, that must be equal and opposite to this force plus this force here. So equal and opposite to 8 sine 20 plus P cos theta. We could write it, if it makes it easier, 3 plus 9 cos 40 subtract 8 sine 20 subtract P cos theta equals 0. And then rearrange it to this. Sometimes that makes more sense to do. So I'm going to rearrange this to give me P cos theta equals something. It's got 3 plus 9 cos 40 minus 8 sine 20. So there's me 7.158. So now I've got this and this to try and solve. And we've solved equations that look like that quite a lot before. It's come up when we've done trigonometry. When we did harmonic form, we had r sine theta equals something and r cos theta equals something. And to solve them, we drew out a triangle like this, where this is P in our case, and this is theta, which means that this is P cos theta, and this is P sine theta. And then I can use some trigonometry to solve it. So P, I can use Pythagoras. We can find out what that is. So it's 7.36. And to find the angle, we can do inverse tan of opposite over adjacent. We get 13.6 degrees. There we are. So same skills as before, just a bit of extra solving at the end on that question. Okay, here's an example of a bit more context to it. So rather than just some arrows on a diagram, we've got a bit more going on. So a picture of mass 5 kilograms is suspended by 2 light inextensible strings. So we don't have to worry about the string's mass, and they're not going to stretch, which makes it easier. Each is inclined at 45 degrees to the horizontal as shown. I'm modelling the picture as a particle, so just as a point. Find the tension in the string when the system is in equilibrium. Okay, so it's not accelerating, is the important thing here, it's in equilibrium. The tension in the strings is going to be here and here, okay, because the object is being held up by the string. There is technically also a force here and here, but this is the force on the ceiling, because obviously there's a force on the picture holding it up, but there's also a force on the ceiling pulling it down. But we're just going to look at this force here. And these are both going to be the same force. The reason why they're both going to be the same is because this is 45 degrees, so it's perfectly symmetrical. So these two values of t must be the same. If these two angles were different, then the two values of t would be different as well. So you could call them t1 and t2 and work them out separately. Now, in terms of solving this, we need to resolve this force into two components. The way that I like to do this, so I'll draw on another horizontal line here. And using alternate angles, so when you get this Z shape here, if this is 45, this angle down here is 45 too. So this is a 45, and this is a 45 degrees. Now we can resolve t into a vertical component here and a horizontal component here. And likewise, we've got the same on the other side too. So we've got a horizontal component and a vertical component. Over here, this is going to be t cos 45 and t sine 45. On the other side, it's the same thing. So we've got t sine 45 and t cos 45. Other forces that might be on this diagram that we haven't put on there yet is the weight. So this weight here of 5 kilograms, there's obviously a vertical force of 5g. Now we can resolve our forces. I'm going to resolve vertically. So I'd have t sine 45, which is this one here, plus another t sine 45. That must be equal and opposite to 5g if it's in equilibrium. Or you could write minus 5g equals 0. And now we should be able to solve this. So we've got 2t sine 45 equals 5 times 9.8. We can solve that to find t. So t is 34.6. If we tried to resolve horizontally, then we would just get t cos 45 equals t cos 45, which isn't very helpful. But resolving vertically, this is helpful to get to an answer. Let's have a look at another similar one. So here I've got an example where the angles are different. We're going to look at how we would tackle it now, because it's not quite as simple now. We've got two different tensions. I'm just going to make this diagram a bit bigger. Okay, so there's two different tensions in the two different parts of the string because the angles are different. And it says the mass is 6 kilograms, so we can draw the weight on straight away. So that's 6g. Then we've got two tensions. I'm just going to call it T1 and T2. Now we're going to resolve them in the same way as we did before. So split up like this. Now this angle here, for the same reasons before, like a Z angle or an alternate angle, this is 60 degrees. This force here then must be T1 sine 60. And this force must be T1 cos 60. Do the same on the other side. So this is 45. So this is T2 cos 45. And this is T2 sine 45. So we've now resolved all of our forces. And now I've just got to resolve them to form some equations and solve it. Let's do vertical first of all. So vertically, I have got t1 sine 60 plus t2 sine 45 must be equal and opposite to 6g. That's my first equation. If I resolve to the right, so looking horizontally instead, my only two forces are this one and this one. So that means that t1 cos 60 must be the same as t2 cos 45. And those are my two equations. Now between these two equations, I've got two variables and two equations. So that's a pair of simultaneous equations that I can solve to find t1 and t2. Now, there's a few ways you could do it. You could actually use your calculator. Your calculator has a simultaneous equation solver in it. You could type in the coefficients of each variable and what they're equal to. But I'm going to do it by substitution, I think. So I'm going to rearrange this to give me t2 equals something. So t1 cos 60 divided by cos 45 equals t2. And I'm going to put that into here. So I've got t1 sine 60 plus, instead of t2, I can write t1 cos 60 over cos 45 times sine 45 equals 6g. And now I should be able to solve this equation to find t1. And when you do that, you should get about 43 newtons for t1. And then we can work out t2 using this expression here. We get about 30.4. Okay. So it's the same strategy as before. Resolve your forces, and then write an equation for horizontal forces and write an equation for vertical forces, and then just solve them. Okay, here's another example. So this time we have a smooth bead. Now the difference between a bead and a particle is that a bead, hopefully we know what a bead looks like, but something that you would thread on a necklace. So it's got a hole in it like this, and you can thread the string through it like this. Okay, this is a bead. If it's just a particle, then it's just a solid object, and the string is connected in two different places like this. And it does actually make a difference which one you use. In a bead, because it's the same piece of string passing through it, the tension in both parts is the same. Here, the particle, and the two tensions could be different because they basically operate as two separate strings. So we've got a smooth bead, so we're looking at this case here. It's threaded on a light, inextensible string. The ends of the string are attached to two fixed points, x and z, on the same horizontal level, basically describing this diagram. The bead is held in equilibrium by a horizontal force of 8 newtons, acting parallel to the z-axis, so horizontal force. Basically, it's just describing this diagram. Find the tension in the string and the weight of the bead. So let's put our forces on. So we've got the weight. Does it tell us the mass? No. So we can just put mg, would be the weight. The tension, we've just discussed that that would be the same in both parts. So this is T, and this is also T. And it's in equilibrium, so all of these forces in total should sum to be the same. The only force I need to resolve is this one here on the right. If that's 30 up there, that must be 30 down there. So this force is T cos 30, and this force is T sine 30. And now we can form some equations to find T and to find mg. In fact, it's just asking for the weight, it's not asking for the mass, so I'm actually just going to write this as W for the weight, because the weight is a force. So let's do horizontal forces first of all. So forces to the right, I've got T cos 30 must be the same as 8. It's a nice simple equation from us. So we can solve this to find T. So it's going to be 8 divided by cos 30. which gives me, as an exact answer, 16 root 3 over 3, or 9.24. Now if we do vertical forces, we have got T, so that's this one here, plus T sine 30. That must be equal and opposite to W. And we now know what T is. So we've got 16 root 3 over 3. I might as well use the accurate answer that I've got there. Times sine 30, which is a half. So now I can work out W. So W is 8 root 3, or about 13.9. And because it's the weight, that is still in newtons. Okay. So you could now be able to have a go at exercise 7b. We've actually done question 1 already. That was one of the examples, and we've also done question 4, but you could have a go at any of the other ones in there. Some of the questions also involve things on slopes, but hopefully you are happy with how to resolve things on slopes from the work we did in chapter 5.